All right. Well, thank you for inviting me here. I really am honored to be brought in and get to talk about my research to you. This is fantastic. Today, I'm going to talk about some of the more popular research that my lab has been doing over the last few years. It's called substrate stratification. You can kind of see right here. We're going to talk a lot about what everyone is taught not to do when you first learn how to grow containers is layering things. And so the whole idea of going back and rethinking what we're told. Um, do I have to go? Let's see. Nope. Keyboard. Nope. There we go. All right. So thank you for the introduction. A little bit just to kind of recap about myself. I am an assistant professor for another couple of weeks. I should have my tenure letter in the mail right now, I've been told, so I'm very happy with that. An extension specialist in commercial ornamental horticulture. I work with the nursery industry. We have a small greenhouse industry in Louisiana, but it's mostly a nursery industry. And I also work with our landscape industry in my extension focus. I'm also the director of the Hammond Trial Gardens. So in my side job, I manage our gardens, which are about a 40-acre garden, doing different trials and evaluations in the Louisiana Super Plants program. But my true passion is I am a substrate scientist. I really look at substrate development and engineering, and beyond that, I'm a substrate physicist. I really, what gets me excited is the water and air balance in a media and hydraulics. And so I kind of want to just talk to you. I think most of us understand what soilless culture is. It's a growing industry, and I mean that in many different ways. But it's just the art of growing plants in containers and not using soil. And so this has been going on for thousands of years. There's pictures of Egyptians on the walls carrying plants. And this was usually initially long ago used to bring plants into the palace or what have you. Mostly this started with citrus, actually, the precursor to citrus in Egypt, and that's why we have orangeries now in like the Middle Ages in Europe. They'd have the glass houses that connected to the houses, and that's so they could grow their citrus even through the winter, and those are our first greenhouses. So that really started it. But in more modern times, the ornamental industry has really initially adopted the containerized as well as production because of transportation. If you're growing a tomato or a pepper, you could just pick the tomato and pepper and sell it. But if you're growing an azalea, you got to move the whole azalea. And that's easy enough to dig, but if you're growing an oak tree, it gets really difficult. So we start growing in containers in the ornamental industry. More recently, CEA ag and protected ag has really adopted soilless culture as we get into more indoor production. And that's really vegetable production really jumped into that. But there's a global shift right now. And so a big increase in soilless culture, really led by small and tree fruit. We also know that strawberries, blueberries, blackberries and raspberries are starting to be grown in soilless culture, but also larger crops. I grow citrus. I do some citrus research. University of Florida does a lot of citrus research in containers for actual fruit production. When I was in Europe, they're growing cherries and all types of tree fruit in commercial orchards in soilless culture. I was at a meeting in France a couple years ago, and they were showing how they're growing sorghum and stuff like that in soilless vertical farms and using less water and getting more protein per acre than they could. It costs a lot more energy in that ways, but it's a really growing industry, and there's a lot of crops shifting into it. A lot of the Asian markets we've seen are shifting into soilless culture, so that's really driving a lot of the growth. And cannabis obviously is all grown indoors right now, or a lot of it is grown indoors, also increasing that soilless culture. So we're growing plants, but it's also a growing industry. Now, this industry relies on soilless substrates. So initially, when they started growing in containers way back in the Egyptian time, but even early in the 1900s, you'd use soil. And the problem with soil, and we'll get into this later, is when you put it in a container, it won't drain really well. And so they'd have to create these substrates, which were really developed in the 1960s, that are very high porosity and low density. So you want water to come out of them, high drainage, low density, so you can move them around. They're pretty lightweight. The container effect, like I said, that is where you put a soil into a pot and it's not going to drain well enough. And so that's why they had to use a lot of different things. Like in Louisiana, we have shells. And so they would grow in actual shells out of Lake Pontchartrain in the 40s and 50s in nursery in tin cans. Now we use mostly organic materials. There's a bunch of CEA that does some mineral wools, but pine bark here in the South and other tree barks all throughout the country is huge for nursery. And then peat moss is usually our #1 substrate media. And globally, it's been the #1 substrate component for the last 60, 70 years. But because these are designed to counteract the container effect, we actually design substrate materials to be inefficient with water. We don't want them to hold water, so we make them really coarse particles. And that leads to really uneven moisture profiles. You can get hydrophobic because they're organic, so they can repel water. And then just the way we produce containers, unless you get into a really large container or in a greenhouse setting, is really inefficient in itself with a lot of wasted water. So these are developed to be inefficient. Our fertilizer is probably one of the more efficient uses of fertilizer with the controlled release fertilizer, but it itself is very inefficient. Just the way CRFs work, if you don't know, they absorb water through osmosis because they're high salts, and then when the media dries out, it pulls the salts back out with it. And so, especially here in the South, it's really hot, so we drive that process a lot. So when you put fertilizer out on a plant in a nursery, even in a controlled release, it's going to dump a load real quick, and that's going to leach. Also, I've never been to a nursery that doesn't have something like this because these pots fall over in rainstorms and all that fertilizer goes. So while it is one of the more efficient uses of fertilizer in ag and soilless culture, it's still an inefficiency. Another problem with the substrate that we're seeing more and more now is it's expensive. I took a picture of this. I don't know if you can see that. $48 for a bag in a retail setting, and I was just flabbergasted. I couldn't believe it, so I had to use this when I say that these media can get really expensive now, especially in a retail setting. And so that's just another limitation to us using it. And then probably the biggest concern we have right now for soilless media is the peat. And if you've been living under a rock, unless you've been living under a rock, you should have heard of the peat issues in the last couple of years. But if you haven't, so peat is what we use. It's harvested out of bogs. And this is one of my students in a native virgin peat bog. And a peat bog is just all different types of plant materials. There's wild blueberries and raspberries and all kinds of different trees and shrubs. But the main component is this sphagnum moss, and that is what we use, peat moss. And this is what it looks like fresh and alive. So it's been getting a bad rep because in the media, that somewhat fair, somewhat unfair, there's both sides to it, because it is not a renewable resource in our lifetime. It does renew, and the peat companies here in the North America do a really good job at restoration once they've used this, but it's a very slow process, about 1 millimeter a year. And I'll kind of show you how much we use in a second. And so it's been getting a lot of poor media and bad press. And whether that's fair or not, that is driving changes in the industry. A lot of the media we get here in North America is based off what they're doing in Europe. So in Europe, the peat is being used for horticulture, but also burnt as fuel, which we don't use. Canadian peat is never burnt as fuel. So they've gone through their peat stores or moving through them at a much quicker pace, and it's done less sustainably than we do here. But unfortunately, people don't really get that, and that's just the way it is. So the Canadian industry, the North American industry, feels the brunt of that. The other big problem with peat is there's only a limited supply that can be harvested sustainably. So it's harvested through these giant vacuums that drive on the peat fields. And so they strip off that top layer, all the vegetation, and this is what's left. You can kind of see some feet. This is how far it goes down. And this machine's pulled, it's a big vacuum, and it's pulled by a tractor, and it just sucks up maybe the top centimeter, and it goes back and forth. And these are heavy machines. Peat is very spongy. You see you have to cut these trenches to drain it out so they can actually do it. And there's only about a 3-month window every year that the peat can be harvested. Otherwise, just the weather's too poor. Well, in the 4 of the last 5 years, they've had really wet seasons because our weather's just changing a lot. There's a lot of variation going on, and that's limited it even further. So beyond all of the peat media issues and the environmental concerns, which may or may not be valid, I'm not going to get into that. Availability is a serious problem because the last couple years we've had under 45% of the quota. And so when I told you about all these additional groups wanting substrates as we shift into fruit. If we have more vegetable production in soilless media, cannabis, different foreign markets and global markets wanting it, there's just not enough to go around. And so that's one of the big problems. Those are the big problems we have right now. This is just a study that I did with a bunch of my colleagues where we really looked at substrate needs into the future to see how all these new markets are driving demands, and you can kind of read some more about it. But what I really want to say is a lab out of Wageningen University in the Netherlands did a really neat study a couple years back to project the global demand of substrate. And with all these new markets coming on, it's a 400% increase over the next few decades. The problem is, like we just said, the peat is what we're harvesting is all we can. They can't just harvest more because they want to do it sustainably. So only a certain amount of fields are opened, and once those are cleaned out, they reseed them back. So they don't want to open up new fields. And there's that limited harvest window. You can only vacuum up so much before the rains come. So peat isn't the answer to grow this. And so therefore we need we need to find different methods to use the peat and use other materials. And so that's what I'm going to talk about today, how some of my research in the stratification is really can help alleviate all those major problems that we're seeing with the growth of the horticultural industry. And I call this a decade's journey because when I was first starting my PhD program, I talked with my advisor, Dr. Jim Owen, who's now with the USDA, and he pitched this: we can solve all the problems within the container. We don't need any of this other stuff. What's in the container, the substrate, touches everything and influences everything that goes on. And I really like that idea. And so he and I have been working on this for about a little over 10 years now, when I was in my doctorate, and then since then in my lab now. And that is just this stratified substrates. And it's very simple. It's nothing too technical, but it's just layering media inside a container. And it allows us to do targeted fertilizer placement. If you can kind of see in this, we just put fertilizer in the top half so you don't get a lot of immediate leaching from fertilizer in the bottom. It allows us to control the air-water balance within the container. Again, we'll kind of get to in a bit why everyone's told you your whole life not to put coarse material on the bottom of the pot. And I'm going to say that that's true in most cases, unless you're doing it for a reason. And it also, we found just subsequently, it improves our crop productivity. And then what I really want to get to, the most exciting part, is how we could use this to fight our peat reliance or reduce our peat reliance. And this isn't, like I said, we don't like to call it a novel solution because this is everywhere. We actually got the inspiration from, you look at golf course greens, they're all layered to manage things, or construction soils, or just natural soil is all in layers. And so can't we mimic this in a container? And the answer is, well, we can. But just to kind of take you through the thought process of how this idea started, and I want to give full credit, it initially started with Jim through my PhD program, looking at fertilizer. That's all we wanted. We didn't want to use different substrates. We just wanted to be more efficient with fertility. And so this is what we typically do. You mix your fertilizer throughout the entire container, and as you irrigate it, the water moves down. So we thought, why not just put it in the top of the container? You're still going to get access to the plant, and as you irrigate it, and instead of losing that initial load of fertilizer, it will just sink into the lower part of the pot, so you'll retain and get more action. And then when you think about the root zone access, it really makes sense. And so this is how the idea started. Not different medias, just different ways to improve fertility. But then, because I am a physicist, I really started thinking about what else we could do. If we're going to, we went to a couple nurseries and looked at, some of them have a 2-hopper system with a conveyor belt where they'll fill half the pot, put a transplant in, and then it'll go down the conveyor and fill the other half. So we said, let's just put the fertilizer in that second pot or second hopper. And so we said, well, why can't we change the media in there? And it was kind of like, of course we can. So there's 2 primary forces that control the air and water balance within a container: gravity and matrix potential. And I'm not going to go too deep into this, but gravity, a taller pot is going to drain more than a short, squat pot of the same volume, just because you have a higher gravitational potential. And then you also have your matrix potential, which is just consider your pore size. So coarse pores drain a lot more than small pores. It's pretty simple. So when you put those 2 together, you get a moisture profile. And every container, homogeneously mixed container, just mixed the same normal way, is going to have a moisture profile where it's drier on the top, wetter on the bottom. And that line could be whatever. We could change it a lot of different ways, but this is what it looks like. So like I said, we do a lot of work where we can screen different particle sizes, and we can move that line to the left or right. We can make it drier and wetter, but it's overall, if you're getting a fine material, you hold more water, but you hold more water throughout the whole profile. If you go with a coarser material, yes, you lose that water hold, increase air, but you do it across the entire profile. So you're not going to hit that good porosity balance that you want this way. But if we change the profile, we put a fine material that's going to hold water on the top where gravity dictates water should fall from, and we put a coarse material that's going to drain water on the bottom where gravity dictates water shouldn't be or should stay, we in theory get a more uniform moisture balance. And so that's the whole point behind the stratified substrates, how we started. And you can really see this is just theoretical representation, but it's the same moisture and air balance, but it's just rearranged in the container. That's why we call it defying gravity. And then here you can just see a little graphic. We want to increase our water in the top, lower our air in the top, and increase our air at the bottom and lower water to be uniform. So we like to say today's soil substrate with this idea behind us can be easily made on site with a nursery where they could just screen out some, it's a low input method just to break your substrate apart and use it the whole substrate, but in different ways. So we did an initial project, it was funded through the HRI to look at this. And so what we did is we wanted to look at our standard in Louisiana. We just use unscreened bark. We get a lot of rain down there, so we don't like to put a lot of different additives in our nursery production. And then we did coarse bark on the bottom of different things on the top, where there's just fine bark, a regular unscreened bark, or we use bark and peat just to increase that water holding on the top. We did different irrigation rates that we tried it out. And you don't have to look too much at this. And we did this all with reduced fertilizer. And so we grew an equivalent or better plant in these stratified systems with less fertilizer, and that was exciting. If you look at our growth, and again, not too much important, these are two different irrigations, but the blue is the control. This is standard what we would grow in nursery in Louisiana, and these are in roses. All the stratified systems either equally performed or outperformed the control with less fertilizer and even with less water. So that was exciting as the proof of concept. It actually does work, and we didn't expect to grow a better plant, but we did. So that was a bonus. I was just telling someone that doing peat reduction work is not always exciting for students because I'm not going to grow a better plant. I just want to grow the same plant with less resources, and it doesn't look as sexy on a figure when it's the same plant, but you're using a lot fewer resources, and that's the fun part. So after that, I have a graduate student, Christopher, who is about to graduate here and start as the nursery specialist at Virginia Tech. So I'm proud of him. And he did a lot of work on stratified substrates. We wanted to go a little more deep into it and look at the moisture application and irrigation rates and see if we could pair specific targeted irrigation with these stratified systems. Because if you think about stratified, we're trying to keep that water on the top of the container. So instead of our one deep irrigation, which we're a lot of times taught to do, breaking that irrigation up into shallow irrigations because we're only trying to really fill that top of the container might give us more results. So we looked at just breaking the irrigation up and again, looking at a deficit irrigation. And these are just different growth indices. Again, don't focus on too much except for the black line, it's a control. And these would all be quality plants in a nursery, and this is what they're going to use. And by splitting the different lines just in all different systems, all stratified plants outgrew the control except for one where they were all the same. So it was never lesser than. And then you get to something right here where this is actually plants dying off. So at a when we have cyclic, so it's just a little bit of water coming 3 times a day on a deficit in the hot Louisiana weather, just like y'all know, those plants are going to start to die. They're not getting enough. So in that really low water, these stratified systems actually continue to grow plants. And so that was what we were really hoping to see, that this was not only growing the same plant with a little less resources, less water, and less again, I meant to mention there's low 25% reduction in fertilizer in all the dotted lines. But we're able to overcome some water stress too, which is how the system should work on the physics level. So we wanted to go a little deeper with Chris's work and really understand the moisture balance within these systems. So we set up tensiometers within a pot and also moisture content sensors to kind of measure the water balance at the top and the bottom of the system. And then this graph, it's going to get a little crazy. So I want you to see that the blue lines are always the top of the container and the red lines are always the bottom of the container. And so what you can see here is just a few days of irrigation. And so you have your substrate tension on the axis, and just the lower it is the drier it is. And again, blue is the top of the container and red is the bottom. And this A is a standard system. So again, the water is being held at the bottom of the container is pretty stable. And that top of the container, you have a lot of flux. When it's irrigating, it jumps up and gets wet, and then it real quickly drains and dries out. And so you have this constant flux. In a cyclic application, you cut the bottom of the container stays about the same, and then you cut down that how wet it gets because you're not adding as much water into it, and so you're cutting down how much it's drying as well. But then on these bottom two is what I really want you to look at are the stratified. So a standard irrigation on stratified, you have pretty close. And then when you do a cyclic, you pair the cyclic with the stratification, right here you get almost identical overlap. And so that is what this is representing, where you have that equivalency where we were looking for, that uniformity between air and water balance in the top and the bottom that does not exist in a standard system. And so that was really exciting to us. This was actual proof that what we thought was going to work in the models actually showed up in the system. So we wanted to go a little further. We wanted to do it more applicable for growers. And so we wanted to look at just single screen. So maybe a grower could just split their bark on, or whatever they're using on site, and use the fines that come out on the top and the coarse materials on the bottom. So we had a few different screens, and we grew some crepe myrtles, and this is growth index, and we see we didn't get much difference. So all the systems grew just the same as the control. But what we saw is it looked like there was a big difference in rooting, and that was kind of exciting. And I appreciate y'all showing around at Texas A&M. You have a lot of high-tech equipment, but I don't think you have as high-tech equipment as we do, where we use our rusty saws to cut these in half. I love this picture because I came out and found my students and I said, you couldn't pick a clean saw, you had to pick that one. And so we cut the roots in half to kind of assess the root growth. And it was pretty impressive. So what you have here, I want to just show you, is the bars are the root mass, the dry mass in these systems. And so these are just the screen sizes, and the controls no screen. And beyond the separating it, just if you stack those two bars, that's the total root mass. And you can see that two of these stratified systems had between 3 and 4 times the total amount of roots in that container. And that was what was really neat to us. So sometimes we'll outgrow the shoot. Sometimes we won't have a difference in the top part of the plant, what you're looking at, but the roots is something we always seen. And this was the first time we looked at it. Every subsequent project we've looked at, such incredible root growth in these stratified grown systems. And I'll kind of get into that later, but it's just a feedback loop from the moisture balance being up high. But that was exciting to us. And so this is probably one of my favorite things. I'm an extension specialist. I had spent, at this point, it was probably 5 or 6 years, just looking at how to reduce maybe 20% of water or 25% fertilizer with all this effort, just hyper-focused. And I was telling my growers, and one of them looked at me and said, we don't care about that. 20% water doesn't mean anything to us. We're in Louisiana. But couldn't we use this to save money on our soil mix because it's really expensive? And I'd never once considered it. I had just talked about putting different things into different hoppers, never once considered just doing something cheap. And my mind just like popped, because in southern Louisiana, we can get bark delivered for $20 a yard, but a commercial peat light is going to be about $200 a yard, maybe a little less if you're buying a lot of it, but it's still a 10 times difference. And I was like, of course. So we decided to set up this as on-farm trial. And we just let him grow his petunia crop, did some stratified. And if you look down the middle, on the left is all stratified, and on the right is all non-stratified. And so he saw that we grew some more compact plants, which we do see early on, a little compaction, which is good. But if you'll notice, all the plants on the right, his standard ones, are flowering, and none of them are not. So I was like, well, damn, I just killed Tony's crop. It didn't work. But turns out in petunia production, you have to stress them out, water stress them to get them to turn on the flowering. And we'd built the system to alleviate the water stress. And so it worked exactly how we wanted to in the stratified system. And they didn't stress out when he turned the water down. So he had to turn it down even more to get them. And eventually they all flowered and he sold them all. But it was really neat to see that concept in real life. And these are some pictures from him. He saw just improved rooting in a standard system. And again, this is something he's completely happy with at that stage. And then this is how much more roots we had in the stratified grown plants. You can see the bark on the bottom. So we did we got a grant from the Fred Glockner Foundation to kind of test this concept. And we just did like a standard peat light over a pine bark, did some more petunia work. And we grew these plants for a few days, or for a couple weeks, and then it got hot. This couple years, last year, the year before, in April, and our controls started to wilt. And because we were doing a watering every 3 days, and the stratified we saw didn't with the same amount of water, which is not what we wanted. This was not a drought stress, so we had to turn up the water for them all because we wanted to let them get the water they needed. But we see a difference in rooting that was really exciting. So this is in stages over time where we'd harvest plants. And you can see this non-stratified, the plant it roots all the way through, and then it fills in, and it's really well-rooted plant. There's nothing wrong with that. But in the stratified, you root just, we call it a piston flow, really, where it roots out and down instead of down and out. And then you get so much more filling in as it fills in and moves down. And so we have such great root mass. And this is kind of just, again, root dry weight over time. And these are the two stratified. We deficit and irrigation, it's not really important. But what you can see is the root mass is the same throughout the project, but most of the roots are located the top half in the stratified, where they're throughout the crop, well, the pot in the non-stratified. So this one basically runs out of room to expand, and this one has a lot more to go. So that was really exciting to us. So Chris's he stayed on for a PhD, which he's doing right now. And he was really interested in the root response to stratification. So he built these rhizoboxes to kind of understand that root growth in stratified substrates and the sequential growth. And he hated doing this, by the way. So I told him I'd give him these rhizoboxes for his new job so he can torture his grad students. But he traced these, and this is kind of neat. So we can kind of see how a stratified system grows root-wise. They start off just at the beginning, and then instantly you can see these stratified, they start to spread instead of go down, where the non-stratified are shooting to the bottom, out shooting to the bottom versus that. And you can kind of see, we measure the rooting angle. It's a much bigger spread. We also did this in actual containers and compared the difference to kind of see how it works, because this is obviously a two-dimensional system. And how it grows, it fills in as it moves down. And so this is you can kind of see these are stratified systems. This is how it works. It fills in on-farm trials and in our controlled research as it moves down, and eventually just gets so much more dense. And so that's how you get it. And so it's a lot of that feedback from that moisture loop. Chris did some frozen column experiments where we grew plants in columns, and then I don't have a lot of data on this, but we segmented it to look at the roots in different areas. And just a fun fact I want to include, just in this column, he uses a program called Rhizovision where he scans the roots, over 32 feet longer in root mass in just this little PVC pipe in a stratified system than in a regular system. So why is it important? He's very interested in root production, and increased root biomass can help with, again, helping with plant stress and good transplant. I have a lot of projects in looking at transplants, shock in stratified grown versus non-stratified grown plants. Quicker establishment, better root health. But the overall benefits of stratification is we can improve our crop growth, whether it's through our roots or the shoots. And we can reduce our water and fertilizer input, and really a reduction in peatmoss. But I think the coolest finding from this is basically that we're not done. There's such little work in the substrate since the 1960s, except for using different materials. We just fill the pots the same way the whole time. And so just this one little idea, and we just keep finding new benefits from it. It just shows that we really need to think outside the box. I was also just telling this story. I love this point because when I was interviewing for jobs, I went to another university and I talked about the substrate work I want to do. And I had a professor that I know pretty well look at me, who was a plant breeder, and say, why would we hire another substrate or production scientist? We figured out how to grow it. We just need new genetics. And I was like, I think we've got enough colors of petunias, but that was just because I knew them enough. And so I didn't want to. But there's so much new out there. That thinking that we know how to do something and whatever it is what I really don't dislike. And it's just always about coming up with new ideas and thinking outside the box. And then I put this in because I really was excited about this because I saw this on LinkedIn. Some faculty out of in the EU were talking about my research. And so it's really neat because I see this stratified work in nurseries in about 15 different states that I've helped here in Texas. There's growers that are growing with stratification and across the world. And the Dutch took credit for my idea. So they tried it 15 years ago. They stopped, and now they're going to relook at it because there's some good work in the U.S. So I really thought that was a great idea, or a great sign when people are starting to say, hell, we did this if we just had to stop for a while. But and they even used our terminology, the stratified. So I thought that was really neat. But that's just something really important that we're not done learning and understanding these concepts. A question that I get pretty often when I talk about was, how do you layer the stratified and how does that work? So we did a couple projects looking at stratified layering and the depth and evaluation. And you can kind of see this is all a peat light, a little bit of 25% of the bark on the bottom, 50-50, and then 75% bark. Obviously not doing too well, really slowing down with too much of that bottom layer. But up to about 50%, we've seen in a couple different crops you can actually get away with. And the really exciting thing to me, this was later in the study, so that one actually does close to catch up. So if you really need to in a pinch, like in years where peat moss is really short, you can get by doing that. But what it means is it doesn't have to be so specific and exact. And growers, when I ask them how to do it, if you can just cut your peat supply by putting a couple handfuls, or if you're hand filling or run it through it, you don't have to exact measure the 50-50 to get, there's no optimal rate is what I'm seeing here. And I'll show you in some roses. It's just, there is a point of no return when you put too much in there, but it doesn't have to be too specific and exact, which is really good because that's what we want for applicability. I've done this with, these are different stratified depths in roses, and looking at different fertilizer rates, and we're seeing about the same. But again, in roses, obviously we're doing coarse bark over fine bark, so it's a little bit different than a peat light over a bark. But you still see about that same, up to about 50%, you're growing a good crop. But what was really exciting about this is in our high rates of fertilizer versus our low rates of fertilizer, not much difference. And again, that was the whole point of maintaining that fertilizer on the top of the container as opposed to losing it. And we get that, we can use a low rate and still get the same productivity as a high rate. Something else I'm doing, and we just started doing some of this work, is looking at plug production. Again, really for two different reasons. The reason I'm interested in is to cut peat. It doesn't seem like it, but plug production is massive use of peat, even in these small cells. And by being able to cut it with perlite, or we do wood fiber to grow equal or similar plugs, really will cut down on that peat reliance. But also, one of my research associate, Maureen Thiessen, is doing a lot of work on this with me to improve our air balance. In a small cutting, it's hard to manage that air and water balance and keep them wet enough and hydrated enough constantly that they don't desiccate, but also have enough airspace. And so we found that stratification, by rebalancing, it gives us a lot more airspace within the plug and actually helps us get more success in woody propagation. So this is something we're just starting to explore and we're excited about. So what's next for stratified? I've got a lot going on. The biggest thing is this idea of using a substrata as a filler material. So I do a lot of work with regional materials, and I'll just talk about that briefly in a second. But really, if we can find a way to keep the high performance, we call like a peat light, as like, I've always heard it as like a a Lamborghini. It's very precision. It does everything you want it, but you got to take a lot of care of it. And then a bark or something that's more like an old Ford truck. It's not going to go too fast, but it's not going to break down. It's going to get you where you need to go. So using these different materials together without blending them, because when you blend them, you lose the unique properties of the stratification. But working on different wood fibers and hardwoods and regional bioresidues and ag fibers and what have you, as substrata in what we're calling a filler strata, so we can still get that high performance of the peatlight, but only use about 50% or less of it. And then we're doing a lot of work on temperature management in containers, and stratification has shown some really unique opportunities. That's what I think the next big idea for us is how we could use stratification to manage temperature within the container. Shelf life, I get asked a lot. You're growing a lot more roots, and these plants sit on a Home Depot shelf. Are they going to wilt faster? And so we actually have a study going on right now to test that. And we are not seeing faster wilt. It's actually, like I said, it helps the plants be more resistant to that drought. And so that's really neat. I wish I had more data on that, but that'll come off soon. And then automation is the big thing that everyone always asks about. And that same group with the Dutch researchers, and then my old advisor, Jim Owen, and myself are working with some companies to look at developing automation technology for greenhouses interested in stratification, particularly in small cells going forward. But what I think is using this filler material, so we just got a grant from the American Floral Endowment to look at using wood fibers beneath the peatlight in commercial floriculture nurseries, and then reconstituting wood fibers back in the top to kind of get an even further reduction of peat. So cut it by 50% in stratification, and then reconstitute it in for even more peat savings. And so this is something that we're working on right now. We've just started our first trials and having some really good results with rooting. So it's not just a bark on the bottom getting the peat and then getting to some other materials. That is hydrofiber, but we're using hydrofiber and a few other wood fibers. There's one just down the road from here that just came, timber fiber, that's working with Harrell's here out of Texas. That's a different way of expanding the wood, but this one is hydrofiber. And just real quick, I'm just going to go through a couple other things that my lab's doing to like kind of mitigate peat use that's not stratified, because I had a few extra minutes. So this is one of my students, Martha, and she's looking at we were up at one of the peat companies in the bogs, and they were telling me they want to do a lot of work with pine bark, and they didn't have a lot of research on pine bark. They're like, we've been using bark for ages down here. Like, we can do that. And so they wanted to use bark as a peat alternative. So looking at different screen sizes of bark and blending it in. And this is just that's a standard peat light, and this is with some bark blended in at 2 millimeter, 4 millimeter, and 6.3 millimeter a quarter inch. You can see just improved growth and productivity. And we're also starting to hammer mill bark. So this is a extensive process of screening out, and you create a lot of waste material. But if we're hammer milling, we take all the bark and just grind it down to 2 millimeter, really 3 millimeters where we've seen as a good target, to actually act as a peat alternative for up to 20 to 40% of the volume, which is nice. I mentioned Maureen Thiessen earlier, but she does a lot of work with me. We use sugarcane bagasse as another peat extender. If y'all don't know, the sugarcane is ground up, and the juices and the sugars are extracted, and this is basically the bagasse is the trash that's left over. It's a really neat fiber. It breaks down and rots really fast, but we did some work on some quick turn crops like osteospermum, petunia, things that are only in the pot for maybe 60, 75 days, and that doesn't have enough time to break down, and really use that up to 40% in our peat mixes to reduce the peat by 40%. And now I want to actually take that and do a stratification with it and see if we can use that in different layers before it breaks down. Wood is definitely the best option we have right now. I think one of the seminar series, in this seminar series, you had Dr. Brian Jackson, who's my old advisor, a few weeks ago or months ago. So I'm sure he talked all about wood, but we're doing some work with Brian I've got a student, Amanda, that's doing woods right now and looking at different species and different processing methods of how the different woods react. And she's doing a lot of microbial work to see that depending on what tree species you use, you get a lot of different results in the wood. And it can be used as a different material, whether you want it as a peat alternative, a perlite alternative, or whatnot, and see how the longevity you need. And so it's not just wood is wood is wood. And this is something that I think the industry wood has just been thrown at us really fast because we've been forced to shift because of the peat shortages. And so it's catching growers off guard to know that the different hydrofibers, the different timber fibers, the different woods, commercially available woods do different things and they're not all the same. And that's something that we're really looking into. And then this was just fun because I just harvested, made this. This is not a peat alternative, but I wanted to put it up here. So we looked at, I've gotten asked by a lot of growers about developing standard operating procedures for potting and how many times to bang it down and what it actually does. And so we just want to do, this is just a regular peatlight at different densities packed, growing a very similar plant, but a lot different in roots. So basically, as you increase your density or pack it down, you go up your root length up to a certain amount, and then you start coming down as you would expect. But you just get the complete opposite in the average root diameter. And so actually a little bit of density does help the rooting. And so that's something that Chris did on a sign project that we were really excited about. Just real quick, because I don't have much time, the last thing that we're doing, and this is probably where my lab is moving, I kind of mentioned, is substrate temperature management. And this is one of my research associate and graduate students, Ashley Edwards, and we've been doing a lot of work with a group of guys at Auburn, Tennessee, Ohio, and Oregon. Myself doing temperature research, and this is, I think, it's so damn hot that these plants are feeling it. And so just some growing, I don't really need to show you that we can grow better plants using a different ways to manage temperature, whether it's container or irrigation. But this is what's exciting, just using a pot, and this is 2 different irrigations, to lower the temperature, you get such a better plant. And then look at the roots, and this is just all temperature response. It's too hot in a black pot. And so something we've been trying to talk to growers is about whether it's using a white pot, whether this is 2 different irrigations, a single or a cyclic to cool the pot down. You need to do something here in the South because these plants the roots are starting to die off at 38 degrees C, and we're at 47, 48 a lot of the summer. And so of course they can't grow. I don't have it, but there's a really cool picture that one of my colleagues, Jake Schreckheis of the USDA did, and he put a big white sticker as a label on a black pot, and we grew some plants, and all the roots grew right behind that white sticker and nothing anywhere else. And I just saw it and I was like, that's insane. But flowering too. This is a standard black with a single irrigation. A little bit, you can use a cyclic irrigation to cool it off a bit more. A white pot with a single irrigation, cool it off a bit more. And then when you combine your 2 tactics we have, pot color and irrigation, you can see how big the flower power can get. And this is just some fun things in hydrangea we did. And you just last real quick, you can kind of see how many hours on an average day these are above that denaturing zone of 38 degrees. With a white pot, you do get over it a little bit, but maybe 40 minutes a day. In a black pot, you could be over that zone where the roots are actively dying for 4 or 5 hours a day in the summer, and that can get really, really tough for the plant. This is just total number. If you look at the hours, this is the hours above 40 in a white pot with a cyclic irrigation over the course of a summer, 50 hours. So that's not too bad, but 250 hours in a normal black pot. And that's just too much for these plants to handle. So I just kind of wanted to stick that in there. And I think I'm out of time. Oh, last thing. So the idea between this was managing temperatures, not just for plant health, but we really wanted to look at fertilizer longevity. And I was kind of tie that back into that initial dump of fertilizer, because fertilizer that we use is so controlled by the substrate temperature and also irrigation to a certain extent. But these are fertilizer releases on different temperature managed containers. And so this black line is a black container. And then the dashed line is a cyclic irrigation. And so you can kind of see that these black lines just instantly drop that fertilizer. Most of the fertilizer comes out in the first month in a black pot. And by using a white pot or cooling it's not just a white pot, by cooling the temperature down by about 9 degrees on average on the extreme temperatures, and that's what these white pots can actually do. You can expand that, delay that release of fertilizer, and this is consider your crop growth so that it actually mimics when your plant is big, when the fertilizer is coming out, or when your plant's actively growing. And so we want to do a lot of work with using substrate temperature and specifically stratification to control that substrate temperature flux to improve our fertilizer efficiency as well. And I think that's the next area we're going to go to. So with that, I appreciate your time. Thank you for coming. I think I have a couple minutes for any questions. Thanks.
I'm going to jump in because I know Dan Lineberger's online and he always tries to ask the first question. So we're going on. All right, I'm going to ask my Jerry Maguire question. You know it's coming.
Yeah.
Show me the money, right?
Mm-hmm.
So you mentioned that some of the research is enabling us to use less peatmoss and meat.
Mm-hmm.
And soilless media, even if you were to reduce peat by half,
Mm-hmm.
and some of the more expensive components of soilless media by half,
Mm-hmm.
that's still anywhere from 4.3 to 4.8% of cost of goods sold.
Yep.
Right? It pales in comparison to labor.
Absolutely.
39 to 42% of cost of goods. All right. So given that, you're to me, one of the most exciting pieces of this is the reduction in shrink.
Yeah.
Particularly at the retail level. That's the most expensive part of in the whole supply chain. That's the most expensive area of shrink. So, and you've incurred all the costs, labor, soilless media costs, etc. And while soilless media has increased 60% from 2007, right before the Great Recession, right? So over the last 14 years, we've seen a tremendous increase.
Oh yeah.
But not nearly as much as the increase in labor.
No, yeah.
So it's that shrink. That's the holy grail right there, trying to minimize that.
Absolutely. And like I say, we try and do a little bit in the labor with the automation, but that's just a whole different level. And I get asked that about my growers about all these things and the money. And at some point I gotta say, hey, I can only control what I can control. And so I'm gonna do what I can to save you money on the substrate, reduce that shrink, help keep those plants growing a little longer, reduce the fertilizer, and then that's the best we could do. Absolutely.
Even in 2021, we could sell anything that was green side up. We still had $168 million worth of shrink.
Yep.
Well, that's a chunk of change. So if you could reduce that by 10%, that would dwarf any savings in terms of soilless media.
Absolutely. Yeah, that is cool. I'll get a slide in there for that for my next talk. Yes, sir.
We have a lot of growers that are struggling with their boxwood production. Have you looked at the stratification with it? Because some of the things that you're talking about, I think it would be applicable because we're seeing disease hit through the heat of the
absolutely.
So early on, we're okay, and then all of a sudden, so that ties in almost with what Charlie's saying with the shrink, because 50, 60, 70%, they're tossing at certain nurseries.
Absolutely. Yeah, we've actually grown some boxwood and they've grown well. We don't have boxwood blight in Louisiana, so I can't really say that it's doing better than that. But even some of the other diebacks that we've seen, that's that moisture balance, that increasing that air balance and moisture balance we have seen anecdotally that it's helped. I've not actually evaluated it, but I've seen and I've talked to people that there is some anecdotal evidence that it does help with some of the disease resistance and especially fungal stuff. But I have not evaluated that. But I do know a bunch of nurseries that I've talked to are very interested in looking at this to really mitigate some of those disease.
We don't have the blight either, but it's all the other things.
Yep.
That it gets, and as soon as the temperatures go up.
Yeah, and I really think just that different ways we can mitigate. So with the stratified, you can really balance that air and water, which helps a lot with the disease. But also anything we can do to reduce that temperature is huge. To just a stressed plant is going to get diseased much easier than a healthy plant. So yes.
Type of bark are you, I'm assuming it's pine.
So most of that is a loblolly bark. Loblolly pine, but we've done studies, I don't have them in here, out on the West Coast nurseries where they're using Doug fir, white fir, lots of different ones, but the vast majority of what we're getting is loblolly pine.
Jeb, you alluded to the fact that bark's fairly hydrophobic, and do you have any problems with, I'm assuming that you include a surfactant in the initial fertility, but do you have any problem with the surfactant running out later in the cropping cycle?
So we do not use a surfactant in our bark-based media in Louisiana. Like I say, we get in South Louisiana, I get about 100 inches of rain a year, so we don't need it. We're actually trying to reduce it. But we have done some work with surfactants in the greenhouse production. And so what we typically do, and we also do this with our lime, it's kind of, I didn't mention it, we just blend it into the upper layer. And we don't really need it in the bottom because the bottom isn't dry. It's drying out more than normal, but it's really being insulated and protected. So we don't even lime the bottom part of the bark, and it's fine because a lot of that nutrient uptake is happening in that upper layer of the bark or upper layer of the substrate. So we do not put any of the wetting agents in the lower part, and we've not had an issue with it.
Very good.
Yes.
I noticed most of the plants that you included were ornamentals.
Yes.
So
That's the
does
best.
sucking out this peatmoss, say for edible plants, does that affect the nutrient uptake of the plant?
So peat moss so I will go on record and say there isn't a better product on the planet for growing plants soillessly than peat moss. So whenever you substitute it out, we're going to get something that's going to break down a little faster. Now, as far as toxicity goes, no, we're not using anything that would have any kind of toxic components, but there's going to be a lot of fertility issues with using things like the sugarcane, using things like even some of the woods are going to break down relatively quicker than peat. So there might be a little bit of that. But the fact is there isn't enough peat, so we got to do something. Something's going to have to happen. So there's going to be some detriment and hits along the way. And that's a lot of what we're doing with wood fiber work is look at different woods that are going to last longer and not have that drawdown on nutrition. But as far as anything that could be dangerous to eat and take up, I have not looked at anything like that. And that's one of the great things about ornamental research. I don't care. Yes, sir.
Any difference with overhead irrigation versus drip?
Yeah. So we do a lot of in the overhead irrigation. It's most of our nursery stuff we do has only been in overhead in our research. And so we do get less of that, what I should say, drought resistance or low water resistance in the overhead than we do in our greenhouse studies with like a little spray stake, because we're getting just more targeted application and you're really getting to see that upper layer, that upper strata work full time when it's getting all the water and collecting. Because a lot of in a nursery at an overhead, a lot of the plants are shaped like a Y and they're just channeling that water down. And so it can actually run down the plant and actually, no, I don't want to say bypass that layer, but it gets down further into the substrate or to the container in a large plant overhead irrigated that's being collected through its foliage than in a spray stake or a drip putting right on the surface. But yeah, with the drip irrigation, the the way the stratified system works and holding that water in the top half, you really get a lot of water savings, or you obviously get more water savings than drip, just efficiency anyhow, but it does exemplify that, yes.
See the green.
chart. No, there's nothing in the chart.
Thank you all very much. I appreciate it.